More survey-ish. I'll cover several things a little bit more superficially, but hopefully at least give some of the technical ideas and innovations in each part. But as always, I'll start out with a little review. It's a good thing I don't give 4 talks because the review would become more than the new content. So, the local Hamiltonian problem, we're given R positive semi-definite matrices on k qubits of dimension d, so they're a finite number of entries on an n qubit system. We're given 2 real numbers, and we want to know is the smallest eigenvalue of the sum of the terms applied to this n qubit system less than e or greater than e plus delta, and our margin is delta is at least 1 over poly. We define the class NP, the class that you can verify correct solutions if you're given the sufficient information, and the quantum analog, where the witness is now quantum, the verifier is now quantum, and we're asking if X is in the language, there's some quantum witness that causes the verifier to accept with high probability. If X isn't, no matter what quantum witness you give it, it will not accept. The probability of acceptance is bounded from above, and we talked about how we can boost these probabilities arbitrarily close to 1 and 0. Containment, Boolean satisfiability is an NP, and the satisfying the witness is just the assignment to the variables that tells you what satisfies that Boolean expression. Similar for local Hamiltonian, we're asking, is there a state whose energy, according to this Hamiltonian, is less than E, and the witness is the state itself. Okay, and we talked about the verification procedure that can sort of verify that with reasonably high probability. And then for hardness, what we want to do is start with a generic language in QMA. Okay, what do we know about it? Well, if it's in QMA, then there's some verifier circuit, okay, such that if X is in the language, then there exists a quantum witness that when we measure, we get one with probably at least 2/3. If X isn't in the language, no matter what I put in here, the probability of acceptance is bounded from above by 1/3. Okay, so that's just the generic outline of the proof, and we showed that this can be reduced to k-local Hamiltonian. So in other words, we can use this circuit construction and the input X to create an instance of k-local Hamiltonian, so that if X is in the language, if the verifier accepts with high probability, then the energy, the lowest ground state of this Hamiltonian is bounded from above. If X isn't in the language, in other words, this circuit will not accept with high probability, then the lowest eigenvalue of h of X is bounded from below. Okay, so the question about whether what the ground energy of this Hamiltonian is answers the question whether X is in the language. Okay, and we did this for 5 local Hamiltonian. And local in quotes, there's no sense of spatial locality here. We're just saying that every term operates on 5 qubits. Okay. Okay, so what was the Hamiltonian? Okay, so this is mostly what we spent lecture 2 on. The most important component is this propagation Hamiltonian. Okay, so it's a sum of terms. And the essential features of this Hamiltonian is that the ground state of this is the history state of the computation. Okay, so it's a uniform superposition of states, and each of those states tells you what time it is in the circuit, how many gates have been executed, and the state of that circuit after that many gates have been executed. Okay, so this is the entire history. We talked about the fact that the spectral gap is bounded from below. Okay, so that a state that tries to cheat and not represent the true computation is going to suffer some type of energy penalty. Okay? And then we had 2 additional terms, one that enforces the fact that the input to the circuit is the X that we want to compute on. Okay? And another one that tests whether the output of the circuit is in fact accepting. Okay, so those are the 3 components. And my final Hamiltonian is just the sum of these 3 terms. Okay, that's where we were. Now we talked about, in the first lecture, I talked about variations on this problem. Okay? Locality is 1, which is the number of qubits that each Hamiltonian term operates on. The other one would be particle dimension. They could be qubits, they could be qtrits, they could be q64ths, whatever, okay, finite, okay. And then the last one, which is probably of more physical interest, is geometry. So I can imagine insisting that the particles are laid out on some type of regular grid and that each term is only operating on neighboring pairs. And this is sort of the physically more realistic picture.
So how locality is different from the geometry? I think if you define geometry, then locality is followed, right?
So the question was, how does locality relate to the geometry? So in this picture that I've drawn here, these are implicitly too local. Okay, so I'm implicitly only operating on pairs that are connected by an edge. Locality assumes nothing about the actual geometry. I mean, I could be operating on 3 qubits, but they could be across the room from each other, okay? All right, so the original proof by Katayo showed that 5 local, 2-state or qubit local Hamiltonian is QMA complete. The next step in this was to actually show that you can actually embed this in 2 dimensions. And that, so 2-dimensional, implicitly 2 local, and then these particles have 6 dimensions to them. Okay, so you can reduce any language in QMA to a Hamiltonian of this specific geometric form. I'm going to say more about this as we go. I'm just going to sort of give you the lay of the land, and then we'll go back and revisit some of these techniques. Question in the back? Okay, so 2-dimensional means that it's in a grid. I can draw it on this board. 2 local means that the terms are on neighboring pairs of qubits only. 6-state means that each one of these blue dots is a 6-dimensional particle. Not a qubit, but a q... Hexit? Yeah. Okay. Okay. Then this was improved to 2 local, 2-state is QMA complete, and then finally 2-dimensional 2 local on qubits, and then to 1-dimensional Hamiltonian on 12-state. And I'm just gonna. This is the set of things that we'll spend some time talking about. I just wanted to give you the landscape. Let me just first say a few things about this. I had it in my mind. It's been a yes.
The 2-dimensional 2 local is 2-state, or?
Yes. This is qubits. I think I meant qubits here. So 2 everything. Yes. All right. All right, so let me just say a little bit about this, and Dory talked about this, I forget whether it was the days blend together, about adiabatic computation, but I just want to step through it again a little bit more carefully. Yesterday?
No, today.
How time flies, yeah. All right, and I was surprised to go back and look at this paper. It had been a while since I read it. This paper, by the way, is near and dear to my heart because it's the first paper in quantum that I understood. It's not the first paper I read, but it's the first paper I understood. So, but it actually doesn't say anything about QMA completeness. This is a paper about adiabatic computation, or the original paper that what I looked up on the archive. I think mostly talks about adiabatic, but there's once you prove one, the other follows. So let me just kind of walk you through that. So Dory talked about the model of adiabatic computation, where you have some very simple starting Hamiltonian, you have some final Hamiltonian, the ground state of which encodes the answer to a computational problem you want to solve. You go slowly over time from one to the other. I've drawn a straight line here where it's the convex combination of the 2, but you could imagine a more complex path. And the adiabatic theorem tells us that as long as your pace is at least as slow as 1 over the spectral gap of your Hamiltonian, you'll stay close to the ground state. Okay, and the final measurement tells you the result of your computation. So you hope to be in the ground state of this Hamiltonian at the end, and there's some measurement that you can perform that tells you is X in my language. Okay? And originally suggested in the context of hopefully solving NP-hard problems, and an appealing model because it may be robust against some kind of errors. And as Dory mentioned yesterday, we know now that this model is actually equivalent to the circuit model. The first step was to show that quantum circuits can simulate an adiabatic computation. And it was this, it was the two-dimensional paper that showed that adiabatic computation can actually perform a computation performed by a circuit. Okay, so, and the basic idea is that this final state is exactly this history of computation state that we worked on in the last lecture. Okay, and just to, so we no longer have a witness in this situation. We just want to know what the outcome of the circuit is on an input. The start state is just the ground state is the all zero state. And I can assume that my circuit, as Tomas mentioned in his lecture this morning, actually sets the bits of the input within the circuit. So my input is actually 0. And the first stage of the circuit just says, okay, I'm going to apply X gates in order to encode my input X. Okay, this just flips the bits according to X. Now I have X, my input, written in binary, and I perform the circuit. And then the adiabatic computation should end in a state that's close to the ground state of this history state. And then if I want to know the answer, I measure first of all the clock register and say, okay, I'm going to measure the clock register. Am I in the last state? Okay. If I measure this, do I get capital T instead of some other time? If I get capital T, that tells me that the computation register is actually representing the output of the circuit. And then I measure, did it accept? Okay. Now this only works with probably 1 over t plus 1, because I could measure this clock and get some other time step, in which case I don't get my answer. So it requires some repetition, but only polynomial. Okay. And there's some extra work. We know the lowest eigenvalue for the spectral gap for this one. We talked about that last time. This is what H start looks like. There's only one ground state, and it's the initial state in this. And some extra work to show that actually any convex combination of these two matrices has a large spectral gap. Okay. So a lot of these results, you may prove it about QMA. It actually has a corresponding result about adiabatic computation or vice versa. So what this paper actually showed is, yes, an adiabatic computation can simulate a circuit, and moreover, that adiabatic computation can be performed in 2D with a two-local Hamiltonian as well. So it's sort of a more physically realistic situation. So not just any local Hamiltonian, but one that actually lives in 2D. Okay. All right. Questions? Yes.
What is the dimension for the final local two-state proved?
We didn't even talk about how you would put those bits in 3 space. It was just a mathematical construct. So I don't know exactly if you wanted to take that and embed it in 3 space how you would do that. Okay, yeah. But there is actually, in this paper, they do that. So in this one, they do that where they take the local one and they actually distribute the clock bits around spatially and address that. So it can be done. You have to add some extra bits, though, when you do it. Okay. But let me talk a little bit about this technique before we get to the 1D. So I want to talk about how we do this embedding in 2 space, because as you just mentioned, the original 5 local state says nothing about actual space and embeddings. Okay. Okay. So the idea is, in this Kataev construction, we have this computation register and this clock register. Okay. And we don't really worry about where they're located. So instead, what we're going to do is take the clock space and distribute it throughout the computation space. Okay? So now a particle consists of, it's a d-dimensional object. It has the ability to encode a qubit, and this would be part of the computation. But it also has these, I'm using colors here, to represent different things about the clock state. So each particle encodes a little bit of the clock and a little bit of the computation, all in one little unit, okay? I've drawn 9 states. The actual result is 6 states. 9 was just a little easier to verify as I was preparing the talk, but it can be done with 6. So every particle has some information about the clock and some information potentially about the state of the computation, okay? So a clock state is just a pattern of colors of these little dots on this grid. So here's N. This is the width of my circuit. And this is time. And a particular state of the clock is just a pattern of colors on this 2D grid. Okay? And it's encoded in such a way. And basically, sort of the idea is that computation is going this way. The fact that these are dark tells you that, okay, we've executed the first 3 gates of the circuit, or we're moving from right to left. These we've gotten to yet. And we're somewhere in the middle of the computation of gate 4. Okay, so the colors of the clock are telling you sort of where you are in the computation. Okay? Yes?
So do you mean we don't need extra particle to record the time state? I mean...
Can you repeat the question so we don't...
So do you mean we don't need extra particle to record the time?
Yeah, so we don't need these separate qubits to regulate time. The Hilbert space of that clock is now sort of infused through the system. Okay, so it's distributed all over the system. So this tells me that I'm sort of a particular time step. So I look at the colors and this tells me that I'm at time, n times 3 plus 1 or something like that. Okay. And some of these particles actually also contain the state of the computation. Okay, so these guys don't because we're done. These guys we haven't got to yet. But this tells me sort of at this point, after executing 3 gates of my circuit, I'm in a particular state of the circuit. Okay, so encoded also in these qubits is the state of the computation. And this is in one column of the matrix. Okay.
But the state could actually be spread in time. It doesn't have...
But we ensure that it's not. So yellow states can't encode a qubit. Black states can't encode a qubit. Only certain colors can, and we make sure that they're localized to one column so that we don't have the computation spread all over this n by t 2-dimensional grid. I know that only some of the qubits are encoding the state of the computation.
But is it something I do? I mean, I wrote a Hamiltonian. The Hamiltonian does what it wants. It will spread time all over the place.
Yeah, and I get to have these local constraints. I get to put in all these terms that say, if you spread the computation, then you're going to have a high energy. So remember, we can make these like forbidden local patterns using an energy penalty term. And enough of those local patterns will ensure that my clock state has a certain look to it. So I can disallow certain clock states. I can allow a qubit here, a qubit there, because it'll have a high energy penalty because of all of my little local constraints that I'm embedding. Okay?
And to your, the spatial dimensions of the grid, right?
Yes, yeah.
So that's the
Yeah.
time and
It's not, I mean, it's
time originally.
Yes.
Time on this system.
Yeah, exactly. So this spatial dimension is representing time. Yeah.
Sadly, perhaps it's worth noting that this is very reminiscent of the proofs with tiling.
Yes, and we use tiling all the time in these. I have slides on tiling, so we'll get to tiling. So it's kind of an old combinatorial problem, and we resurrect that.
New heads, yeah.
Yes. All right. Tiling has a new life. So, yes, there was a question in the back.
Well, I don't completely understand what we did here with the colors. We added qubits that have only clock bits on them.
Mm-hmm.
Like additional qubits.
So this particular particle here happens to be in a state right now that doesn't encode a computational bit. Earlier, it might have been in this green state and encoded a qubit.
But we still have all the qubits encoding computations entangled with clock states. So we just added qubits encoding just
Yes.
we added more like blank time.
Yeah, actually, yeah, here it is. So some of these states don't encode, some of these clock states don't encode a qubit, and some of them do.
So we just added columns of computations with extra like empty time.
Yes. And we need that in order to sort of have time progress from left to right. Okay, so you know, I actually have a little actual action where it kind of propagates, so that might help a little bit. Okay, so one type of terms we have are the type of terms where we sort of say that certain configurations are forbidden. These are just energy penalties. So for example, I can't have a yellow state to the left of a black state without incurring some energy penalty.
That's penalty for the clock.
Yes. And then I have these propagation terms like we had before. They're just looking a little bit more complicated. So what this says is I have a propagation term that says if I'm in this state, if I have white here and green below, that will transition to this state with white below and orange up here. Okay, so now that tells me that there's a propagation term that says the amplitude of this state has to be equal to the amplitude of this state. Okay, and I can also, in the course of that, notice that these qubits encode a qubit. I can actually enforce that when this propagation happens, I'm actually triggering the execution of a gate. So these are the diagonal terms. This is forward propagation. This is what it was. This is time t minus 1. This is time t. I execute a gate. This is time, t plus 1. T plus 1 back to t. I undo the gate. Okay, so it's the same type of thing. Just I'm using sort of this different schematic for the states of the qubits. And we want to make sure that, again, that we apply all of these forbidden states and carefully pick these propagation terms that so I'm using these forbidden terms to just totally rule out certain patterns of dots. Okay, so I know that certain patterns of dots will never happen. Okay. Other patterns of dots are valid. Okay, so I can do this same kind of configuration graph that we had last time. So last time we had this configuration graph on all the possible clock states. Now I'm just looking at clock states. And a clock state is just a pattern of colors on the grid. Okay. And I'm going to draw, so every vertex in my graph represents a standard basis state of the clock, just a way of mapping colors to the dots, okay? And I'm going to have an edge between two if I can go from one to the other by one propagation term. So this is the same configuration graph that we had before, just the states that they're representing are a little bit more complicated, okay? And we have this same pattern. So we have a set of valid clock states that don't incur these sort of localized, that satisfy all of these localized constraints. We want to make sure that we go from the starting state to the final state, okay? Then we have a bunch of states that sort of represent totally arbitrary patterns of colors, and we want to rule those out. Those are ruled out by the local constraints. And so those all have at least an energy penalty of 1. So it's the same graph. I'm just representing the clock states differently in this sort of spatial color pattern. Okay?
So this one's even for the 5 local?
This is 2 local because, oh, sorry. So this was, you're asking if this is still 5?
For the 5 local one, or is like a 2?
This is 2 local because the propagation terms only need to operate on 2 of these particles. So every term takes 2 particles and transforms it into another set of
But
2.
this 2 local is only for the propagation.
Yes, and all of my forbidden, so I have two types of terms. These ones that sort of forbid certain configurations, those are all too local. That say, you know, I can't have a yellow to the left of a black, for example. And then the propagation terms are all too local. So everything is too local here. Okay?
When you have these an edge denoting like a propagation, doesn't the column containing the computation need to shift one to the right?
Okay, so let me actually go through this. This was a lot of work, so I'm going to go through this and maybe it'll answer your question. So we start out here. A propagation term applies. The little white qubit moves down. Now the propagation term applies to this kind. And each one of these is triggering the execution of a gate. Apply the execution of a gate. And now we need to copy the qubits over, which is exactly what I think you were asking. Okay, so that's what the next little set of things does. So now the propagation term applies to these two. I copy the qubit over. I move up. I copy the qubit over. Okay, so does that help answer your question?
So essentially there could be several gates operating at the same time.
Yes. Well, yeah, so as I sweep down, as long as the gates are ordered 1 to 2, 2 to 3, I could be executing multiple gates on the way down, but they have to be on wires, qubits 1 and 2, and then 2 and 3, and then 3 and 4 all the way down. Question in the back? Yeah, so the question is, when I'm going down, are the gates, they're done sequentially, but I can only have a certain pattern of gates. 1 and 2, then 2 and 3, then 3 and 4, all the way down. And then I copy the qubits over as the little cursor propagates up, and then I execute another row of gates, 1 and 2, 2 and 3, 3 and 4. And any circuit can be, with polynomial overhead, transformed into a circuit that has that special pattern, 1 and 2, 2 and 3, 3 and 4, all the way down. I should have drawn that circuit, but I didn't. Okay. All right? And there we go. And then we start again. Okay? So that's a little bit of an overview of how that, obviously there's a lot of details in sort of how you're picking these 2D terms and ensuring that, you know, for a valid clock state, only one propagation term will apply at any point to make sure that that configuration graph has the structure that we want. But once you have that, sort of all of the other machinery, the lower bounds on the eigenvalues and such, they just apply. Okay? Okay, so let's now move to 1D, and yes, question in the back. The last time solution was not in 2D? Well, we didn't even actually mention anything about space. I just assumed I could grab any qubit and any 5 qubits. And so when we talked about it, there was sort of a computation register here and a clock register here, and my 5 local terms grabbed 3 clock qubits and 2 computation qubits. We never showed that that couldn't be embedded in 2D space, but we never even worried about it either. So I was grabbing clock bits and computation bits and applying terms to both. Yeah, so now we'd like to take that and put it in a more realistic setting of a Hamiltonian that's sort of embedded in a 2D grid. So that's sort of the work of this fancier clock state. Yes?
So actually related to that question is, so last time we said we have to do these 3 local, sort of like from one state to just you have to do the 3. You can't do 2. If you do 2, there's some other edge coming out.
Yes.
But here you're actually, in the Hamiltonian, you're doing 2. Why?
Yeah, so in the last talk, I talked about the fact that the way the Kitaev construction works, you can't just go with 2 local terms on the clock state. And it's because these are higher dimensional particles that we can get away with 2 local. So the clock is actually encoding more information. There are 6 possible colors for these dots to be. So I can sort of, I can actually restrict my...
Yeah.
Yeah, so I'm, as Nati said, I'm trading locality for dimension. I'm putting a richer amount of information in each of these particles. Yes?
Why we need 6-state particle? I mean, what if it's just 4-state or 5-state?
It's possible. We don't know. So 6 is what worked for this construction, 6-state particles. We don't know that 5-state isn't possible. As far as I know, it's not ruled out, right? So it's all they could do. Yes.
Did you say there was a follow-up to this with qubits?
Yes, and that's a different. There is a follow-up that does it with qubits, but it's a more sophisticated technique with sort of perturbation theory, and it's not like this. Yeah. Okay, question in the back, and then I'm going to go on. The 2-dimension, okay, so this is representing time. Actually, that leads in perfectly to the 1-dimensional construction, which is what I was going to talk about next, okay? Okay, so just a little bit of background about this. The 1D result was a little surprising for a couple reasons. First of all, in practice, we don't have even good classical heuristics to find ground states in 2D. Whereas in 1D, if you ask a physicist, they'd say, oh, 1D's solved. We know how to do that. Because there are such successful heuristics. And the most successful one was invented by my colleague Steve White at UCI called DMRG. So it works incredibly well heuristically in practice. Okay, so in some sense, it's considered an easier problem. Also, the classical analog is in P. If I give you, sort of classical states and it's diagonal, every Hamiltonian term is diagonal in the standard basis state, then it's a classical problem, and we know how to do it in 1D in polynomial time using sort of dynamic programming or divide and conquer, such. 2D classical is NP hard. Okay, so one might expect that sort of difference to show up in the quantum, but it's the fact that superposition gives us sort of an extra dimension that allows us to encode a hard problem in a 1D Hamiltonian. So it's the extra dimension is sort of this quantum superposition that we get. So in the first lecture, I talked about the special case of the local Hamiltonian where each local Hamiltonian term is diagonal in the standard basis, in which case the solution is just a classical state. It's just a string of assignments to each particle. Okay? That's what I'm talking about in the classical problem. So, yeah, it's a constraint satisfaction problem. Each one of these circles can take on one of D values. For each pair, there's a cost depending on what the colors are, and then I want to find the way to color this line as to minimize cost. Okay, and you can encode that. That's a special case of local Hamiltonian. Okay, so in the 1D, we're basically taking this grid and laying it out on a line. Okay, so each one of these n qubits is now laid out from end to end here, and I'm marking these the boundary between two patches of n particles with special states, and I can do that by just special local Hamiltonian terms that says this particle has to be in a blue state, this particle has to be in a yellow state. So I can actually sort of mark out these smaller configurations using the local Hamiltonian terms. Okay, and so I'm just going to sort of hint at how it goes. There's obviously a lot of details in terms of what the propagation terms actually look like. But the basic idea is that we have always an active site. Okay, it's like a little cursor. And the propagation terms only apply to pairs that have one of those little cursors inside them. And that ensures me that I'm not going to be able to apply a propagation term somewhere else in this chain. So if I have a valid configuration, then there's only one place where the active site is, and that's what the Hamiltonian term will apply to. And it basically it moves over 1, it triggers the execution of a gate, and then the cursor moves over to the next position. Okay? Once it gets to this end, now I have a problem because I have to move all of the qubits over. So that's exactly what this little guy does. It's a lot of work. He runs back and forth, shuttling the qubits back and forth from here to here. Okay? It's kind of like a Turing machine, you know? And the details are sort of like a Turing machine too, in terms of into the amount of work it does. So you copy everything over, and then again it slides to the left, from left to right, executing the gates. Okay? So that's sort of the rough idea. Obviously the details are not that interesting, kind of like Turing machines. You just sort of argue that it can be done. Although when you write the paper, you do have to argue that a little bit more specifically. So the n qubits move over and you continue. Okay? There's one difference with the analysis here is that we can't outlaw in this construction, we're not able to outlaw invalid clock states with local terms, all of them. So what we have is this configuration graph. Here's our valid clock states. Here's this messy graph with invalid clock states. And we have some of these chains with a bunch of valid clock states and then an invalid one in the middle, okay? And we want to sort of argue that any state in here is going to have high dimension or high energy, okay? Daniel called this the Clairvoyance Lemma because from here you're sort of looking ahead and seeing that if I execute propagation, I'm going to end up in something that has a locally bad configuration. And it's a matter of showing that you need to lower bound the lowest eigenvalue of the sum of these two matrices. So if I look back and look at one of these chains, the propagation term of the Hamiltonian gives me this. The fact that one of these configurations has a high energy cost gives me this matrix, and I have to show that the sum of the two has a small eigenvalue. So it's slightly different because we have to sort of outlaw these other states. Okay. I'm going to... All right. So we had 12 states per particle. It's been improved to 9, I think is the current state of the art. So one of the problems with this is that what I mentioned earlier, you're really encoding every single pair and every single qubit to have its own special local Hamiltonian term. Okay? When physicists study systems, they don't look at, you know, these two atoms have this Hamiltonian term and these two atoms have this Hamiltonian term. Basically, they pick a model, which is the local energetics between two neighboring particles, and they apply that same term to every local pair in their grid that they're studying. So that's a much more physical model than this highly engineered thing where every pair of locals, 17 and 18, have a different term than 18 and 19. Okay? So question is, what happens when we have this, what we call translationally invariance? So let's try and formulate this, first of all, as a computational problem. Okay? So how hard is it to find ground states of translationally invariant quantum systems? So now I'm thinking of the term, the single qubit term, as fixed. It's part of the description of the problem. I'm studying like the Heisenberg model or the Hubbard model or something. So it's a fixed 2D term once and for all. It's not part of the input to my problem anymore. Okay? The only thing I get as input is the size of the system. Okay? And now I'm asking, when I take an n by n grid or 1D line of, let's say 1D of n particles, and I apply this one Hamiltonian term to each pair of particles in this line, what's the ground energy? And so I'm also giving, as part of the input, two polynomials. I'm guaranteeing you that the ground energy is at most P of n, or at least P of n plus this little gap term here. Okay? All right, so with a new problem, we need a new complexity class. So now notice that the input to the problem has shrunk dramatically. Okay? The input to the local Hamiltonian problem is polynomial in the size of the system, the number of qubits, okay? Now the input has shrunk by an exponential factor. The description of the system now is logarithmic in the size of the system, okay? So we need a new class to describe this, which we call QMA X complete. So here's QMA. We've seen it many times before. And now we're just allowing witnesses to be exponentially long and the verifier to take exponential time, okay? Notice that the problem didn't get harder, the input got smaller, okay? So it's still polynomial in the size of the circuit, but since the input is now exponentially smaller, we need exponential time, okay? Now, another thing that we need is we move from the circuit model to the quantum Turing machine model, okay? Why do we need to do that? I think that's, and we're now asking the probability that the quantum Turing machine accepts versus rejects, okay? So why do I need to do that? Hopefully I say it on the next slide. So let's look at what a reduction is going to look like, okay? So I take some generic language in QMAX, and I'm translating the language into some finite Hamiltonian term, okay? This is constant size. This is fixed once and for all. It doesn't get to grow with the size of the input. So everything I know about my language has to be encoded in this term, okay? Circuits, by their nature, are big objects. They grow with the size of the input, okay? So to describe a circuit, I need it has to grow with the size of the input. Whereas Turing machines are a fixed description of the language. It's a finite thing. You know, I set the rules of my Turing machine, and it works for any input of any size. And so that's why we had to sort of move to a quantum Turing machine model, is because we're encoding everything we know about the language in this finite Hamiltonian term. Okay.
In some sense, if you talk about circuits, then it is always something, right?
Yeah.
But like we're reading in a circuit, just tell you what's right.
Okay, so
It doesn't even make sense to ask any questions. Because H is big.
yeah, it wouldn't work at all because we don't have, the question is, does this problem even work in the circuit model? I guess is sort of the, does it even make sense? And I don't think so, because we don't have the space to encode a polynomial size circuit. I mean, the input is just telling us the size of the system and nothing else. So it's not, you know, all of the information about the language has to be sitting here.
But can't you talk about exponential size circuits?
But still, even, you know, there are these, in regular complexity, there are sort of these inefficient descriptions of circuits, but they still grow with the size of the input. So they just grow, you know, logarithmically. So now this has to be fixed once and for all. I don't think, yeah, okay, let's talk about it. Okay. Okay, so we want that there exists a witness that causes my quantum Turing machine to accept with probably at least 2/3, if and only if the n-particle chain on H has bounded ground energy. And similarly for any, if it's non-accepting for any witness, then there should be a lower bound on the ground energy, okay? So the translation invariant local Hamiltonian executes a process. And here's a high-level description. So we're, again, using these propagation Hamiltonians that sort of give the history state of a process. Instead of the execution of a circuit, it's the execution of a quantum Turing machine. So every step of the quantum Turing machine has a state. And here's what it actually executes two processes back to back. So we're doing this reduction. So I'm describing this Hamiltonian term that has this property. So I'm reducing my instance to a particular size and describing how this Hamiltonian term encodes the answer to this question, okay? And again, the Hamiltonian term will be one of these history state computations, and I'm describing what that computation is, okay?
But just a more bird's eye view, Sandy's proving her remarkable result with Daniel Gottesman, that shows that it's hard. The problem in 1D is hard. I don't know if you're doing now in 1D, but
Yeah.
in 1D is hard even if all you know, if all you are given as an input is the size of the grid, of the lattice. So meaning that the system is extremely sensitive to just the length of the lattice. It's hard to decide what's going on because once you change the length of the lattice, things completely change.
Okay, so here's the process underlying that we're encoding in our Hamiltonian. The first thing we do is count the number of particles in the system, and I'll say a little bit more about how we do that. And then we write n, the length of the system, as we're counting it, in binary in the state. So you think of that as the input to your Turing machine. So you're translating the length, the physical size of your system into a string that tells you how big your system is, and then that's the input to your Turing machine. Okay? So the binary counter Turing machine basically goes and just, there's a Turing machine that starts with 0 and just continually increments the counter. Okay? Just goes on and on, incrementing the counter. And so I have some function that tells me after n steps of this counting, very simple-minded binary counting Turing machine, what's going to be written on the end, on the tape at the end. There's some overhead in executing this addition every time because you may have to sweep over log n bits. So it's not going to be exactly n. It's going to be n over log n-ish. Okay? But it's computable. Okay? So this is the reduction. If I want to know if x is in the language, I'm going to find the n, the size of my system, such that after n steps of the Turing machine, I end up with x written on the tape. Okay? And then this will be the input to the verification. Okay, so that...
The input is capital N.
The input is capital N, yes.
So here, what is
F is this function that just that takes this silly Turing machine, this counting Turing machine, and basically tells you after n steps of this Turing machine, what are the bits that are sitting on the tape of the Turing machine. Okay? And what I want is I want to have x, my input, that I'm curious about, sitting on the tape of the Turing machine. So I'm going to pick n to be however many steps it takes in order to get x sitting there on the tape at the end. So I didn't completely hear.
So if x is like a small n bit string,
Uh-huh.
then the reduction gives you a 2 power n times to the Hamiltonian.
Right. So I think what you're saying is that the size of the system is exponentially larger than the length of the input that I'm getting.
That is visible every such string of small n bit string. Any small n bit string is mapped to like 2 power n.
Yes. Any string of my choice x, there will be some capital N that's exponentially larger than the length of x that will give me that x. Right? So the ground state of H is the computation state that simulates the process of doing this counting, writing the size of the system in binary, and then executing the verifier on that input. Okay? So we need a clock that counts the number of particles in the chain twice. One for this guy, because we want it to run for n steps. And then we simulate the quantum Turing machine on input x for n steps. And then ask, did I accept? Okay? So here's what a particle looks like. And you know it's a theoretical result when you don't even count the dimension of the particles in the paper. So you can think of the Hilbert space as having layers. So each particle is like a sextuple that encodes different things. So we're using this space for multiple purposes. Two of them are the clock state. This is the quantum Turing machine tape. This is the the track that handles the head location for the counting, this is the head location for the verification, and this is where the quantum witness sits. So there's a lot of information that's encoded on top of each other throughout this thing. Each one of these is a particle, okay? Or the things denoting the left end or the right end. And my clock, which I'm just going to sort of describe in just a sentence or two, has a second hand. This is the active site that just shuttles back and forth. It just goes back and forth. And this is the minute hand. Every time the active site passes this boundary from green to purple, it advances the clock. Okay? And that's how I count to n. I know I've gone n times when now this whole line of circles has gone from purple to green. Okay, so it's a unary clock. So to actually get from 1 to n requires n squared steps, because each one of these requires this little particle to shuttle back and forth. Okay? Yes? Did you have a question? Right. That's why it's big. Then, yeah, and n goes this way. N goes this way. Yeah. Okay. So, and again, physicists tend to be less focused on finite systems and are much more interested in what happens in the infinite case. Okay? So, so we looked at the problem and from the point of view of, so let's say the Hamiltonian term is fixed once and for all, and I'm interested in the energy per particle if I apply that Hamiltonian to the infinite grid. Okay, so this is a much more natural physical problem. In 2D, you can have two different terms. You're allowed, even though it's translationally invariant, you're allowed a different term for the horizontal direction than the vertical direction. So for example, how hard is it to determine the energy to within the nth precision on the infinite grid? And to determine energy to the nth bit of precision, you actually only need a finite chunk of the grid. And you can argue that the error that you get from truncating is smaller than a certain amount. So it's still sort of a finite problem. Even though we're looking at the infinite grid, if you're only asked to compute it to within a certain precision, you can look at a finite chunk. But once you move to the infinite grid, you have more possibilities for hardness. So you have the possibility actually to prove that things are undecidable because you have an infinite space that you're working with here. Anything on a finite grid is going to be contained in p space for where p is the number of particles. Okay, so and that was what these remarkable results by Cubitt et al. Did in the next step. So they actually said, prove that if I give you a Hamiltonian term, okay, determining the spectral gap, so determining whether the Hamiltonian has a constant size gap or has a continuous spectrum, is actually undecidable. Okay, so here H, this two-particle term, is the input to your problem. Okay, I give it to you and I say, okay, so if you were to apply this H over the infinite grid, tell me, is the Hamiltonian gapped or not? Okay, and that's an undecidable question.
Space of Hamiltonians, you fix a dimension, there is space of Hamiltonians, a finite dimensional space. Now it's divided in two pieces. One which gives you gap which doesn't go to zero, and the other gives you gap which continues spectrum. Therefore, you're telling something about a subset in finite dimension space. Now, there is a lot of work on this in complex dynamics. When you just take very simple function, x goes to x squared plus c, and some points behave one way, some points behave another way. There's a lot of very interesting pictures there. So do you expect this kind of description, which is, it doesn't make it simple, but it can embed it in the existing algebraic structure in finite dimensional space.
So I think that's essentially what they do is that they're taking two Hamiltonians and well, the Hamiltonian itself is encoding this computational process, but I'm not sure I completely understood the question. You understood the question better, so yeah.
Well, I don't know the answer. I mean, David is talking about some repetitive application of some map, and this is not exactly the same thing, but it sounds like eventually you'll have something like a phase diagram of gapped versus gapless, which might have these highly complex, I don't know, fractal structure, etc., that David was talking about in classical maps.
I think he was asking whether this structure may be
Embedded.
simple in some way, just like
Yeah,
it's
so
not, it's not simple, but that, well, there is a, what you are saying, you define some subset in finite dimensional space. Say when your gap doesn't go to zero.
Okay.
You say this subset is very complicated. The fact that it's undecided, let's say that nobody is.
Yeah.
But it means it's very complicated subset. Now we can ask, do people have kind of classical way to construct complicated subsets? And they do.
Yeah.
This kind of Mandelbrot things, very simple motions. Asking questions, what goes in the limit. Describe very complicated subsets. So I'm asking whether you can kind of ask the question whether your very complicated subset is some simple classical description.
I can answer this. In fact, I convert this question to a question of
Even the moderator isn't following the rules, so.
In fact, I think it's basically right, because the method that Qubit and Wolf, etc., use is to convert the question to a question of undecidability of tiling.
And underneath this whole structure is this very beautiful sort of aperiodic lattice and tiling. So, what's my time like?
You have another 5 minutes.
Okay. So, so the first thing they do, I'm going to just kind of sketch what they do very quickly. The first thing they do is that they reduce energy density to spectral gap. So in other words, what they want to find out, so the energy density is if I take my local Hamiltonian on an L by L grid, look at the smallest energy eigenvalue and divide by L squared. So this is the smallest energy density on an L by L square, and I let that L go to infinity. So this is the energy density in the thermodynamic limit, okay? And I want to determine, is it bigger than a constant? Or is it zero, does it go to zero as L gets large, okay? So this implies that the overall energy is infinite, obviously, if each particle has a constant energy density, okay? So in the interest of time, I don't think I'm going to say too much about it, other than sort of the basic idea is they have two different Hamiltonians, okay? And it's engineered in such a way that HD is some gapless translationally invariant Hamiltonian. There are a dime a dozen in physics. You can pick your favorite one, okay? And they engineer the spectrum so that the spectrum of my big system is the spectrum of this, the one I'm wondering about, the energy density, plus this continuous energy spectrum, okay? So the idea is that an energy eigenvalue for this is taken by taking one from here and one from here and putting them together, okay? Now if the smallest energy density here is less than 0, then that means that this spectrum sort of covers the 0 point, and I don't have, it's all continuous here. So I'm taking this infinite spectrum, or this infinite continuous spectrum, and sort of placing it right here, covering the 0 point, which means it's not gapped. Okay? On the other hand, if this guy has a lower bound of a constant, that means it has an infinite energy, and all of these energies sit way above 0, exposing some simple Hamiltonian that has a gap in it. So they're either placing this continuous spectrum to cover 0 or to be larger than 0, exposing sort of a discrete gap. So that's not sort of, this part is the easy part, so the more interesting part, I'm going quickly here, sorry. This is still this reduction, so I just want to move on. Okay, so now the name of the game is to determine energy density, okay, since we did this reduction. Okay, so what they want to do is you want to have some, this universal Turing machine on input n, okay, and you want to reduce it to a Hamiltonian term that is gapped from below if the Turing machine accepts, and approaches 0 from below if the Turing machine doesn't halt, okay? So this is just sort of the basic plan for the reduction. You've got this undecidable problem that you're mapping onto whether the energy density is at least a constant or goes to 0, okay? So that's sort of the overall structure. Here comes the tile. So the basic underlying structure is this old problem called Wang tiling, which is basically a classical version of local Hamiltonian. So we talked about the 1D version where you're just assigning colors to dots on a line and you're paying a price for various pairs of colors along the way. This is just a 2D version of it. So for every pair of tiles, I have a cost of putting one color to the left of the other or putting one color above the other. And I'm asking for a way to tile the grid that minimizes the cost. Okay? So the construction makes use of this very beautiful set of tiling rules that when applied to the infinite plane creates this aperiodic structure. Okay? And the aperiodic structure has these sort of increasing size squares. So the squares are of 4 to the k by 4 to the k, and the periodicity, I see one of these squares with frequency 1 over 4 to the k. So each one of these squares is actually a square of tiles. And so this is an old sort of result on tiling, is that for a finite set of tiling rules, the lowest energy tiling creates this very special pattern of interlocking squares. Okay? And the essential thing that we need is that I'm having squares of different sizes and different frequencies. So for every k, I have squares of size 4 to the k by 4 to the k at a frequency of 1 over 4 to the k. Okay? And so basically laying on top of this tiling space is the computation. So on one of these squares, on the north edge of one of these squares, I'm now going to embed a computation, a 1D computation, which is sort of modeled closely after the 1D construction that we just saw. So each one of these squares hosts a computation of a given length. Okay? And the idea is that, let's see if I can get to the punchline in a minute or two. Let me just say it in words. Let me go back to my picture. So it's hosting a computation. And so the computation runs for a certain amount of time. If it accepts, there's an energy cost. Okay, so if there's a point in time where, let's say, the computation accepts in less than time 4 to the k, then every square of size 4 to the k is going to have an energy cost. And that will give me a constant lower bound on the energy density. If the computation never accepts, no matter how big these squares are, there'll never be that energy cost, and it'll be 0. So that's essentially, I see a couple of people nodding, so at least I had to go fast at the end. So, but that's essentially the idea. But they make use of the 1D construction in this process.
Your time is up.
And my time is up, yeah, so,
Register it.
okay. Should we just finish or any questions, or you're the moderator, so.
Yeah, sure.
So this is the 2D construction, if I understand correctly, and can you hint about what they do in 1D?
For the infinite, I don't know exactly how they replicate the Robinson tiling in 1D. Do you know? Yeah. Yeah. Yes.
There is a connection between local Hamiltonian and condensed matter physics, and also between condensed matter physics and quantum field theory. My question is there a direct connection between local Hamiltonian in this computational sense and quantum field theory?
Connection with quantum field theory and the local Hamiltonian?
If there are some application of this theory of local Hamiltonian complexity, specifically in quantum field theory?
I don't know. Yeah.
You want to address this, Dorit?
Dorit, do you have something to say?
Well, this whole direction is sort of an engineering way, or a computational complexity plus engineering way to approach the question, what's the complexity that this Hamiltonian encodes? And with the sequence of results that Sandy presented, this gets closer and closer and closer to actual physical questions. So we have translation invariant, fixed Hamiltonian, 1D, and we ask whether the question about a particular Hamiltonian, which is physical, whether, for example, computing the lowest energy, is hard or not. So this also talks about the possibility of hardness in quantum field theory Hamiltonians.
What is the relativity?
The relativity, that is the problem of trying to combine I mean, this is the task of quantum gravity, right? I don't know.
No, because quantum field theory is the union between special relativity and quantum theory. And I don't see...
I think this is question
Okay.
is getting
This is
more
awfully-
involved.
yeah.
Let's leave it for the
Yeah.
break. And the last question.
Oh, can you explain me of the motivation of Wang tiling a little bit more?
Like the original motivation from the 60s.
No.
Or how it's used here. So you have this infinite grid, and we want to embed these sort of finite computations in this infinite grid. So where do you embed them? So the tiling gives us this substrate. So to tell us, like, okay, I have this square here. This, I'm going to put a computation here. I have a smaller square here. I'm going to put a shorter computation here. So it sort of gives you the structure of where all these different computations that are embedded in this infinite plane, where they're going to go. Yeah.
Just can we say just one more word about it? The big open question is really, can we understand the phase diagram of this set of finite Hamiltonians? Is it stable? Is it continuous? How does it look?
Yes, I think it's a great
Yeah.
question. Thank you.